Hello. Hello. Hey everyone, let's get started. Our first presenter today is Mariam Kazarouni. She got her bachelor's from Sharif University in 2010 and her master's from the University of Windsor in 2012. And right now she's working with Professor Overby on geomagnetically induced currents.
Thank you. Good afternoon, everyone. My name is Mariam Kazarouni. My presentation is about model validation for geomagnetically induced current using real data. In this presentation, first I will give an introduction on geomagnetic induced currents, short in GICs, and I will explain their negative impacts on the network. Not motivated by the negative impacts, I will present GIC modeling as the first and basic step to protect the network from the negative impacts of GICs. Finally, I evaluate the accuracy of this model based on some real data GIC measurements. So what is geomagnetic induced currents? The activities at the surface of the sun disturb the magnetic field around the Earth's surface. By Faraday's law, these magnetic field disturbances induce voltage potentials on a transmission line. Now, if we have two groundings at two locations in the network, we would have a complete path for current, and geomagnetic induced currents, or GICs, will flow through the line. I should say that GICs are DC currents, so their calculation and modeling are totally different from the regular GIC, regular power flow formulation which we have in power system, because that one's AC, this one's DC. Did you make up that display or not? The picture? No, it was in the internet. Yeah. So GICs have negative impact on the power system. The most significant impact is the half-cycle saturation of transformers. This figure shows the magnetization curve for a transformer. So the x-axis is the magnetization current, and the y-axis is the magnetic field intensity. Now, under normal operation, the magnetic flux has a sinusoidal curve like the blue line you see here. And for this magnetic flux, the magnetization current is this small blue line you see here. So at a normal operation, the magnetization current has low values. Also, it is sinusoidal. When GIC passes through the transformer, it shifts the magnetic flux curve up, like the red line you see here. And this time, the magnetic flux reaches saturation level. So the magnetization current goes really high, like this area. And when the magnetization current is high, the reactive power loss in the transformer increases a lot. Also, if you look at this red line here, you see that it's not sinusoidal anymore, and it has high harmonics. So how does half-cycle saturation of transformers affect the network? So we said that half-cycle saturation increases the harmonics and the reactive power loss. Now, in power system, reactive power is coupled with voltage. So when we have a lot of reactive power loss, the voltage will drop. On the other hand, we have static VAR compensators, or SVCs, to provide the reactive power for the network and compensate for the reactive power losses. These SVCs are connected to the networks through some relays which are sensitive to harmonics. So when we have a lot of harmonics, these relays may unintendedly trip the SVCs. So the SVCs are disconnected, and the network will lose reactive power support. So this will bring the voltage well further down, and these two together can cause voltage instability, and in the worst case, system collapse. So this is exactly what happened in 1989 Quebec blackout. In March 1989, Hydro-Quebec network went down because of a geomagnetic storm, and the blackout lasted for about 9 hours, and it cost tens of millions of dollars damage to the utilities and the customers. So this is the plot of the Quebec network. So we have two generation units up in the north, and most of the loads are in the southern part. This is how the blackout happened. First, three SVCs were tripped, one after the other because of the high harmonics in the network, which were caused by half-cycle saturation. After losing these 7 SVCs, the network lost a lot of reactive power support, and the voltage went down. As a result, that generation unit was disconnected, so the network lost almost half of its power supply. Following that was voltage and frequency instability, which caused the other generation unit to be disconnected as well. So with no power supply in the network, of course, the whole network went down few seconds later, and it lasts for 9 hours. Now we get to the GIC modeling. So in the previous section, we explained how GICs can affect the network, and we understood that GICs can be very problematic, so it's very important to protect the network from GICs. To protect the network, the very first step is to calculate the GICs on the power line, and that's what my research is about. So in my research, I focus in two problems. First, how to use the magnetic field data to estimate the electric field, then how to use this electric field estimation to calculate the GICs. This figure here shows the magnetic field observatories in North America, which measure the magnetic flux density in real time. So we can use this data to calculate the electric field using this equation that you see here. So we can get the electric field based on the magnetic field and the Earth's surface impedance. Now I want to explain what is the GIC model. Here I use this example to show how can we derive the GIC model. So let's say we have a 4-bus system with 2 generators, 2 transformers, and 1 transmission line, and we enforce an electric field to this network. And that electric field is, of course, induced because of a geomagnetic storm. So we want to calculate the GIC on the transmission line. How do we do that? For that, first we integrate the electric field over the length of the line to get the induced voltage on the line. Once we have that, we use a DC voltage source to model this induced voltage. We also put all the resistances in the network, like the line resistance, the transformers resistance, and the grounding resistance, and that would complete the network. The equivalent circuit. Once we have the equivalent circuit, we just use Ohm's law, voltage divided by resistance, to get the GIC. So it's pretty simple. For bigger networks, we use the same idea. So again, we have the electric field. We integrate it over the lines to get the induced voltage. And once we have the induced voltages, it's like we have a network with a bunch of DC voltage sources and a bunch of resistors. So we use basic rules like Ohm's law, KVL, and KCL to calculate the GICs. And because the system is linear, once we do the math, it turns out that electric field is related to the GICs through some constant matrix, which we call the coefficient matrix. And this coefficient matrix depends on the network topology and the resistances. So if we have the information about resistances and the network topology, we can actually calculate the coefficient matrix. Also here I said that if we have the electric field, we can calculate the GICs. This model, we can actually go the other way too. So if we have the GIC, we can calculate the electric field. So when we were working on the GIC modeling, we were able to get some real data GIC measurements and use that to evaluate the accuracy of our model. So American Transmission Company gave us the GIC measurements for 5 of their substations near the Wisconsin-Michigan area for the geomagnetic storm which happened in March 9, 2012. So this figure shows the location of the substations, and this figure shows the data which we got. And we use this data to evaluate the accuracy of our model. For that, first we use this data to estimate the electric field based on the GIC model. On the other hand, we got the magnetic field data that's available by United States Geological Survey. So we also use that to estimate the electric field, and then we compare these two to see if they match. The more these two estimations match with each other, the more accurate the model is. So to use the GIC model, we need the coefficients, the coefficient matrix, which I explained before. So for that, I said that we need the information about the network topology and the resistances. And luckily, we have that available. So we use that to calculate the coefficients for our substation, which you see in this table. The information which we got was quite accurate, except for the substation grounding resistances. Substation grounding resistance is the resistance of the ground underneath the substation, and that depends a lot on the soil condition. So it's hard to measure it accurately, and we don't usually have that available very accurate. So we got some data, but we knew that it's not very accurate. To account for this inaccuracy, we assign some scales to each of the substation, and we multiply these scales by the coefficients. So these scales kind of associate with the ratio of the actual grounding resistance to the grounding resistance which we had available and was not accurate.
Where did you get the H matrix?
So we had the base case for the eastern interconnect. So we used that. First, we enforced an electric field in east direction, and we calculated the GICs, and then we enforced northward electric. I have a slide, backup slide to show it if you want to, or we can go later.
Okay.
So yeah, I used that test case. Yeah. So yeah. And yeah, I was saying that these scales associate with the ratio of the actual grounding resistance to the assumed grounding resistance.
I have a quick question. So I have you wanted uncertainty only on substation grounding resistance. In the sense, do you have accurate transformer running resistance from ETC, or is that also derived from the Eastern Interconnect model?
So these scales, we actually can estimate it based on the GIC measurements which we have. And the only reason we're only considering this kind of inaccuracies is that we know that this exists. Like, we know that the grounding resistance is for sure not accurately available.
So the S unknown?
Yeah. I mean, they are unknown, but you can use real data measurements to estimate them. Yeah, because it's the ratio of the actual grounding resistance, and we don't know what is the actual one, so there's no way like we can calculate it. Yeah. So this is the magnetic field data measured at Fredericksburg Observatory for the same geomagnetic storm in March 9, 2012. The two figures on top are the magnetic field. So the left one is the magnetic field in north direction, and the right one is the magnetic field in east direction. We use this magnetic field data to estimate the electric field, as you can see in the two figures in the bottom. We also use the GIC measurements to estimate the electric field. And then we compare these two estimations, as you can see here. So the red line is the electric field estimated by the GIC measurements, and the blue line is the electric field estimated based on the magnetic field data. So if you compare these two, you see that they match quite well. For sure, there are some mismatches, especially between time 5 and 6. But like for the rest, the agreement is quite well. There are many factors that contribute to this accuracy, to this mismatch and the model accuracy. The most important one is that we're measuring the GIC measurements at the substation near Wisconsin and Michigan, but we're getting the magnetic field data for Fredericksburg, which is quite far from the Wisconsin area. So I think that's one of the reasons that we're getting this mismatch and not very good accuracy. For example, we were able to get some GIC measurements for some of the substations which are much closer to Fredericksburg, and we did exactly the same test, and here it shows the the result for this substation, and you see that this time the agreement is much better. It's because
What are your units on E field? They seem too little.
yeah, actually I normalized them. Yeah.
Normalized to what?
Well, this one I just like scale them to 1. This one I think it's like the norm 2 of the electric field.
Yeah, put units on there when you can, because otherwise
Yeah, okay.
you get confused.
Yeah, okay. Okay. So, and these are the scales which we use to account for the inaccuracies in the substation grounding resistance. Yeah, so here the x-axis is the substation number and the y-axis is the scales. And we got these scales through some GIC real data measurements. And to have a better...
Back to Wisconsin now.
Yeah, we're back to Wisconsin. Yeah, sorry. So, and to have a better estimation, we used the GIC data for 3 different geomagnetic storms. And here you see that for all of the storms, we're getting the same scales, which is good. The interesting observation was that at substation 1, we're getting 0 scale at all the storms, which means that our GIC model is kind of excluding this substation from the model. So it's like we're not including this GIC measurement at substation 1 to estimate the electric field. So we try to understand what is the reason that this substation is included. For that, we looked more carefully into the GIC measurements at all the substation, and we observed that the measurement at the substation 1 is showing a different behavior than the other 4 substation. So like if you compare these 4 plots, you see that the peaks kind of match, even the timing and also the shape of them. But like if you look at this one, you see that it's just showing a different behavior. And to show, yeah, it's like substation 1, yeah. And like to show this more quantitatively, we also calculated the correlation coefficient and we got the same result. So for sure, substation 1 is showing less correlation with the others. Now, if you consider the geographic location of substation 1, you see that it's all the way up to the north. So we're thinking maybe substation 1 has a different electric field than the other substation. And in our GIC model, we assume that the electric field at all of the substations are the same. Maybe that's the reason that the scale for substation 1 is getting 0, so we can exclude this substation from the model. Oh, and I should say this is still a guess, like we're still working on it and trying to validate it and get better results. Yeah, and to summarize, I presented the negative impacts of GICs on the network, and then I explained GIC modeling as an important part of the GIC mitigation program. Then I evaluated the accuracy of this model based on the real data measurements. Thank you.
Nice job, Miriam. Go back to where you had those S's. Oh, wait. The storm one again. Next.
This one?
No, that one.
Oh, okay.
Just as a point, when you're showing integer data, change your
Yeah.
scale so it doesn't show.
Half, yeah.
And then kind of put a box around your storm 1, 2, 3, so it
Okay.
doesn't look like it's. Okay, that's not the point. Go back. Back. What exactly were the S's are variables that you're estimating,
Yes.
right? Okay. And what are you doing? You're multiplying the whole row in H by S?
Yes. So H matrix is a n by 2. So we have northward coefficient and eastward coefficient. We multiply both coefficients by the same scale.
And your S values came out to be.
That plot.
Go back to where you show the S's.
This one.
Yeah, Dead River aside, that's puzzling.
Yeah.
What would you have expected them to be if you had perfect data?
If we have perfect data and if all the grounding resistances are accurately available, we would have the same scale for all of them.
Would it be 1?
Here we set it to be the sum of them to be 1. So like if we have 5 substation, it would be 0.2 for all of them.
I mean, they seem like they're too far away from each other.
So yeah, that's only when the grounding. So
Yeah, I know about the numbers. So,
yeah,
good.
I mean, yeah.
Other questions for?
I'm just curious what the
sorry.
scale of the DC currents are. I mean, is it like on the order of thousands of amps? Like what
So yeah, so it would be different. Like for example, at one of the substation, it's changing from -40 to 20, and like for some of them, it's smaller. So it depends on the coefficients. I mean, at different regions, they're more or less. So like
In a bad spell, they can get up to.
yeah.
So I'm just thinking from the perspective of like these DC transmission lines that people are talking about. I imagine. I mean, intuitively, it seems like it would have more of an effect than on AC lines. I don't know. What do you think?
Oh, on the DC lines.
Would it cause more problems or the same amount of problems?
So
Because you don't have these harmonics.
well, actually, I'm still not sure if we would have DC, like GICs passing through the DC lines. So, do we? Yeah, we don't.
Another question?
Yeah, so my question was, is there anyone who's building contour plots of density across the world or across North America? Or either plot density or change of density?
Yeah. Actually, yeah, I did it myself too, and there are other people doing it too, and like you can even have a dynamic model that like shows in a video, like to show the whole geomagnetic storm over the whole U.S. So we have that, but like I don't have it here.
So you said that you did that. Was that based off of those 10 points in North America? Or?
So, did you say GIC or the magnetic field?
The magnetic field, because you said that a big problem is that your measurements are really far away.
Yeah. So.
I feel like you don't need to use measurements. A different way of sensing it, and then extrapolating it down.
Yeah. So yeah, we have like the measurements here. So one way to go is to like to find the magnetic field at the intermediate area is to use like some kind of like linear interpolation. But like yeah, we haven't done it yet. So but like yeah, that's the way to go. Yes, I didn't like because I was just looking for the others to see any closer one. I knew about the Frederickson. The most important one, yeah.
The one I used is it not there?
Yeah, I should add that one.
One more question. Is there like a term, like a safety factor? Because like if I have a transformer that's not being used very much, and I see 20 amps of DC, it's a really big deal. But what if I have a transformer that's like nearly saturated and it's like on the verge of being exploded, and then I get 40 amps of
yeah.
So is there like in this study a safety factor or some term you say like, okay, a GIC of this is okay, this certain maybe?
I think they're working on that. So you can come up with operating procedures that say like, for example, during a geomagnetic storm for this severity, under like previous measurements that like this specific transformer will be under stress and like maybe just from before like the geomagnetic storms which happened before. So like you can come up with that kind of operating procedures, but like yeah, but like I haven't seen one, but like there should be one for sure. Yeah.
Is that something that they do now to keep like a headroom, some sort of like headroom on the transformers and additional capacity just in case?
Sorry, I can't hear you.
Is it something that they do in practice now to say like to keep a transformer from being fully loaded just in case, kind of like reserves?
Reactive power doesn't. It's not a question how heavily loaded it is necessarily. The reactive power losses on the transformer don't depend necessarily on the loading of the transformer. They depend on the GICs in the transformer. But yeah, if you derated your transformers, you could do that. But a lot of the transformers that are most at risk are the ones at the generator. So those you put them in place because you're going to operate them at maximum loaded. So usually you don't. I mean, it's on the GSUs that you have the most trouble, and normally they're heavily loaded. You could back down the generation to reduce the loading on those transformers. So there are operational mitigations that can help out.
Yeah.
Is that from like, what is the, I guess, like the detection versus the storm after it turns? Like, is there like a big headway between we know it's coming and it's already here?
I think like once this is because of the activities at the sun, so they observe that, and it takes about 3 days to get to the Earth. So they have like about a 3-day, like they know it ahead of that, and also once it hits the, like for example the measurements near the Earth, then we would know it for accurate, more accurately about in like few hours, like 4 or 5 hours. So yeah, that make them like be prepared for it.
Actually, what Miriam said is true. Mostly for a little storm, it'll come in at maybe 1 or 2 million miles an hour. So it takes, like she said, 2 or 3 days to get here. The big storms can get here in less than a day.
Oh.
There's a satellite at the Lagrange point, which is about 1 million miles from the Earth. So if a fast storm's coming in, it would be coming in at several million miles an hour. So it would be here within 20 minutes of being detected at that point. But even when they come off the sun, you don't necessarily know how bad they are. And by the time they get to the Lagrange point, you learn more about the severity, but you don't even know if it's going to hit the northern hemisphere or the southern hemisphere. So one of the concerns here is if you had a big storm coming in and you took proactive actions that were severe, like shutting down the grid, and then it hit the southern hemisphere and you just shut down the North American grid, you might go, oops, that wasn't good.
Is it better safe than sorry, right?
Yeah, maybe. That was really good.
Thank you. Yeah, I can hold it for you.
So our second speaker is Yu-Tian Lei. He got his master's from Cambridge University in 2012, and now he's working with Professor Palawa on switch capacitor converters. And as a side note, he just took his call earlier today, so don't give him a hard time.
Thank you, Sumin. Hello. Yeah. So it's time for some circuits. Because I originally signed up this seminar. Can we go full screen? Yeah. To hoping that I can get a practice for my call, but turns out that I use my call to practice this seminar. But okay, I'll do it again. Never mind. So the topic of my presentation is soft charging operation of switch capacitor DC-DC converters. Just a quick outline of what I'm going to talk about today again. So I'll give you an introduction and background on two types of converters, the magnetic-based converters and switch capacitor converters. And I'll compare the advantages and disadvantages of the two. And in that process, the motivation of our research will be discovered, and I'll then introduce the soft charging concept of switch capacitor converters, followed by some experimental results, and finally the conclusions. So to start, so DC-DC power converters, they process power from a DC voltage source to another. So there are a few desirable traits of a power converter. I've listed 3 of them here. They are high efficiency, high power density, and low cost. So if we look at the power density of power converters in the past 35 years, and that is plotted as the blue line here, we kind of spot a trend here that the power density of power converters doubles about every 10 years time. Now, if we compare that with the Moore's law, which is saying that the density of information processing transistors, that density doubles every 2 years. So you can see there's a huge gap between the two. By the way, this plot is really normalized at 1975. So there's a huge gap between the two. So we really want to increase this power density further and faster. Now, to improve power density, we can either improve the switches. For example, now we have gallium nitride switch, silicon carbide switch that are beginning to be commercialized. We can also shrink the passive component sizes for like capacitors, inductors. Another way to do that is to look at the circuit topology, is to see whether we can find a better circuit topology that is able to utilize the switches better, that is able to utilize the inductors and capacitors better. And that is the focus of our research. And if it's not already obvious from the title, we are going to look at how switch capacitor converters will improve the power density. So before I go into switch capacitor converters, I'll talk about the buck converters. So buck converters, as we all know, they're very simple. People understand it pretty well. They're very robust. So we'll use that as a kind of baseline for our comparison. But there are two major problems with the buck converter. The first is that it has high device stress. So a device stress is defined as the voltage blocked by the switch when it is open times the current conducted by the switch when it is closed. So if we look at this buck converter here, for example, when S1 is closed, the voltage across S2 is V in. And when S1 is open, the voltage across S2, the current conducted by the S2 is the whole output current. So the device stress is really V in times I out. And if we compare that with the power processed by the converter, which is V out times I out, and the ratio is defined as the stress factor, that turns out to be V in over V out, which is the conversion ratio of the voltage, of the power converter. So we can see that even though, for example, if we fix the output voltage, so as the input voltage increases, even though we're processing the same amount of power, the size of the transistor also has to go up. So this is really the major drawback of the buck converter, which means that they can't really operate in a very efficient manner and in high frequency when the output voltage is really high compared to the input. Input voltage is really high compared to the output voltage. And another problem with buck converter is that they have very poor energy density. So to convince you of that, we'll give you this plot which shows the energy density of the components. It's in millijoule per millimeter cube. And we really want to be on the far right-hand side for a larger energy density. There's really no y-axis here, so we just put the inductors on the top, capacitors on the bottom. So as we can see that the capacitors, so these are just different type of capacitors, different type of inductors, and the values are taken from commercial surface mount components. So you can see there are like at least two or three orders of magnitude difference. So which means that if a converter is able to use capacitors as the energy storage element, it will have a distinctive size of advantage compared to a converter that uses the inductors. And such a converter is called switch capacitor converters. So here is a very simple 2-to-1 switch capacitor converter. It has two phases of operation. So in phase 1, switch 1 and 3 are closed. So this V-in is in series with the flying capacitor and the output. In the other phase, C2 and C4 are closed. So V-in is open circuited, and this C-fly is just in parallel with the output. So as the converter switches between these two phases, a steady state voltage can be established. So for the flying capacitor, the voltage is half V-in. For the output voltage is also half V-in. So that is how it achieves voltage step down. So we can see that first there's no inductors here. It uses this flying capacitor to transfer the energy from the input to the output. So it tends to have higher power density, and it's easier to integrate into an IC. it also tends to have higher efficiency at high conversion ratios, and that is because now these voltages, they only have to block half of the input voltage, because of the presence of this capacitor, all of the switches only need to block half of the input voltage. And if you compare that with the buck converter, which has to block, for which the switches have to block the full input voltage, these switches can be made smaller, can be switched at a higher frequency. And at high conversion ratios, this advantage is even magnified, because now the switches only really have to block a fraction of the input voltage. And this actually has been shown by Dr. Seaman there. So that is all good, but of course, switch capacitors converters have their own issues. Otherwise, we'll be seeing them everywhere. The problem is, number one, as it has poor energy utilization of the capacitors, and number two, it has very poor output voltage regulation capability. We'll go through each of them to see where the problem originates and to see how we can improve on that. So to see why switch capacitors have very poor energy utilization, we have to analyze a very, very simple, the simplest form of of switch capacitor converters. So in phase one, the voltage just charges up this capacitor. In phase two, the capacitor just discharges to the load. So it's not even meaningful, but it's just a one-to-one voltage. It's just a one-to-one switch capacitor converter. So if you look at the capacitor voltage waveform, it will rise from, this is like rise to the input voltage and then discharge to the output voltage. Now, if you look at the capacitor current, you'll see that it has a huge spike of current whenever you transition from one phase to another. That is because we're really shorting the voltage source and the capacitor. And when that happens, there's going to be a voltage mismatch between the two, and the voltage mismatch will be dropped across the series resistance. So that will actually cause an energy loss given by C delta Vc squared. This delta Vc is just this capacitor voltage, change of capacitor voltage in each cycle. So we can see that we really want to minimize, if we want to minimize the power loss, we really want to minimize the voltage ripple of the capacitors. However, if you think about the energy utilization of capacitors, which is defined as the energy transferred by the capacitor in each cycle divided by the maximum amount of energy stored by the capacitor. If you think about it, the capacitor transfers power by charging and discharging. So if you want to transfer a large amount of power, you have to but you have to, the ripple has to be large. It has to charge to a higher voltage, discharge to a lower voltage. So now, if you want to increase the utilization, you really want to increase the ripple. So there's a trade-off between these two, and that can be shown here, can be seen here, where we plot the efficiency with the energy utilization. So for example, if we want like 95% efficient, that is not bad for a converter. We really only utilize 10% of the capacitor energy, the energy that is stored by the capacitor. So even though capacitors, they have much higher energy density compared to inductors, normally we can only use 10% of that, which means we only transfer 10% at a time. So, and if you want more, the efficiency suffers. So that is, so this actually offsets the advantage of the high energy density of capacitors. So we really need to solve that. And the other problem is the output voltage regulation problem. So the switch capacitors, the conversion ratio is really determined by the topology, so you can't really change that. So for example, just now we showed the 2-to-1 switch capacitor converter. That output voltage shown as V out nominal. So the nominal output voltage is like just half V in. So if you want to reduce the output voltage, the only thing you can do is to increase this output referred impedance. So I mean, this is not a real resistor there, but this is a model of the switch capacitor, and it has an output impedance. So you can do all sorts of things, like changing the modulation, the switching frequency, changing the duty ratio, changing the RDS on the switch, but all these will create excessive power loss. They are all the same. They just increase this resistance. It's just like a linear regulator. So in here, we are showing efficiency versus the output voltage divided by the output voltage is normalized according to the nominal output voltage. So you can see that if we want output voltage that is half of the nominal voltage determined by the topology, the efficiency actually drops to 50%. So I mean, a low power, I mean, this is actually the reason why switch capacitor converters are only seen at low power applications, because at low power, maybe this efficiency is acceptable, but if you go to high power applications, this efficiency will create lots of power loss. You can't really, I mean, it costs money, and you will have trouble to cool the converter. So yeah, this is another problem. So the motivation of our research is really to combine the benefit of the switch capacitor converter and the buck converter. So we really want a converter that is able to use these low voltage switches, just like a switch capacitor converter, and we use capacitors as the energy storage element as far as possible. And also, we also like to improve the energy storage utilization. And also, we want to regulate the output voltage, just like a buck converter, without loss. So that is what we have done here. So the concept is called soft charging. So what we have done is to add this additional inductor in a switch capacitor topology. So this is just a Dixon's. So there are so many different kinds of switch capacitor topologies, just one of them. So this is called the Dixon switch capacitor. And what we did was just add a single small inductor there. So this inductor serves as two purposes. The first is that it controls the charging process of all these capacitors. So actually, with the inductor in there, we can operate this converter at a much higher voltage ripple across the capacitors without hurting the efficiency at all. So it decouples the efficiency and the ripple. So the other purpose is that if we switch the switches in a clever way, we can actually achieve lossless regulation of the output voltage. I'm not going to show the details here. But actually, there are many different topologies. We also derived a method that is able to analyze arbitrary switch capacitor topology and is able to tell you whether this technique is suitable. Because for some switch capacitor topologies, you can't really benefit much from adding this inductor. And we actually discovered for this Dixon switch capacitor, we have to change the capacitor size a little bit to let it approach soft charging. So that was the schematics, and this we actually built an actual converter here. It uses an 8-to-1 Dixon switch capacitor converter, which means that the native conversion ratio is 8-to-1. So you have 80 volts, output will be 10 volts. We use gallium nitride switches because we really want to push the energy, the power density of the converter. The power stage is only here. It's actually very small, and the rest are just control, and level shifting. So this converter is able to operate with the input voltage of 200 volts, and the maximum power is 100 watts. So, and switching at 250 kilohertz. Here are some experimental results. On the left, we are showing unregulated operation. The efficiency in unregulated operation, that means we fix the conversion ratio. So whatever the input voltage is, the output is an eighth of that. So we can see that it's pretty good. Its peak efficiency is 95%. Actually, for this kind of power density, it's really good. At light load, the efficiency is smaller as expected because of the switching loss. But it doesn't really depend on the input voltage, so it's pretty good. So we also look at the regulated operation, meaning that we fix the output voltage to a certain voltage, and we increase the input voltage. So the native conversion ratio is about 8, and because of the power loss, even in unregulated operation, it is slightly larger than 8. Now we just increase the input voltage and try to regulate the output voltage, and that is the efficiency we got. So you can see that it doesn't really drop much. But compared to an ideal switch capacitor converter, that converter is like a linear regulator, so this efficiency will drop kind of linearly. It's not very linear, but you can approximate as a linear drop. So for example, at 12, if the conversion ratio is at 12, the ideal switch capacitor goes below 70% efficiency, where we can still maintain efficiency at 90%. So that shows the advantages of this converter compared to a normal pure switch capacitor converter. So just conclusions, what we have done is that we managed to we built a hybrid converter, and we managed to combine the benefits of a switch capacitor converter and buck converter. So yes, we used low voltage switches, and we are actually using smaller capacitance compared to the switch capacitor because now with the inductor, we improved the energy utilization of the capacitors. Of course, we added a small inductor, but actually we found that the total volume of this capacitor and the inductor is still smaller than the switch capacitor's converter. The capacitors in the switch capacitor converter. So we didn't trade off any power density in there. Also, we can do lossless regulation just like a buck, almost just like a buck converter. So therefore, this resultant hybrid converter really is, compared to the other two, it really has higher power density, higher efficiency, is able to regulate the output voltage. But I'm not trying to sell my converter here, but it's really good, and especially in the applications where you want high conversion ratios, high voltage step down, like 200 volts to 10 volts input, 200 volts to inputs, this is really good converter. Okay, any questions? Yes.
I don't know how the cost of power transmission works, but is it any more expensive?
This particular converter is indeed very expensive, but
the labor was cheap.
That is only because of the choice of switches. You can build switch capacitors with these switches. You can build buck converter with these switches. So itself, it doesn't add more cost to the other topologies. Yeah, it's just we're really trying to push the boundary, so we use very good components. That's it. Yeah.
I have a question.
Yes.
How is this different than connecting a switch capacitor converter directly to a buck?
Okay, so the soft charging concept was first demonstrated by Professor Pilawa, who used a switch capacitor topology and a buck converter and the second stage buck converter. So just as the inductor, the buck converter also does control charging of the capacitors. But of course, I don't want to say it's bad, but
Well, I hope yours is better.
So with that actual converter, the buck converter has to run at a higher frequency to look like a constant current source to the switch capacitor. So you added two switches, two switches, and they are switching at high frequency. So there's some penalty on efficiency already. And also, yes, and also because this port now has very large ripple, your buck converter has to try really hard to get a steady DC voltage at the output. You have to use both feed-forward feedback control. It's very complicated. In this here, we actually switch all of them at a medium pretty fast frequency. So we only need an inductor. Fundamentally, there's no difference because the reason why buck converter is able to do soft charging is because of the inductor in that buck converter. So, yeah.
It makes sense.
Yeah. Yes.
Just to be clear, so the implication here is the reduced density, decreased power density. So with this hardware, is that kind of not the main goal? It's just proof of concept?
Sorry?
Was like the purpose of your hardware just a proof of concept to see if the topology worked as expected, or did you really focus on getting the power density?
Oh, it's kind of proof of concept because this is the first time we are using this technique. Besides Professor Pilawa's original idea. But we also try to really, I mean, we use very good switches to improve the power density. But I mean, this is still work that is, I'm still doing some further work, which I really want to show. For example, in this efficiency plot, I really want to show a switch capacitor that is the same as what I mean, this guy is already, it is a switch capacitor converter. We just modify it. So I want to show that without modification, the same switch capacitor converter will have lower efficiency and will have lower power density as well. Yeah.
The reason why I asked that was because I guess I don't know how you find power density. Is it output or like your converter power divided by the size of the capacitive?
Yeah, it is. I agree. It is very tricky actually. That's why whenever I say I didn't really appreciate any paper that try to compare the power density of two converters. I think it's very hard to compare. That is true.
Add your name on PCB
Yeah, that is right. So
like, what is your footprint like?
So what I'm aiming is that the sum of all the volumes of my components are smaller than in this approach than their original approach. Yeah.
There's one of two ways. You can take the volume of every component and add them up, and then you get that total volume. Or you can do the closed box volume. Probably the fairest way. You take a box, but that means you have to do a careful job of making sure everything fits in that box, right? But I think the sum of components is probably the most fundamental metric.
Yeah.
But it's hard because a lot of those things on his board are connectors, that sort of extra stuff that isn't really hard. Well, you said in this design, it was smaller. The size won't pass, it's probably smaller than you only did.
Yes. So you can actually, this is one of the huge capacitors, and this is the inductors. So one inductor there, and there are like a few capacitors. Without modification, this capacitor there will be 4 of this large size. So we actually reduce the size of capacitors, even though we put one inductor there, but that is only half the size of that one capacitor. Okay.
I think you guys have been tested enough today.
Thank you.
Right? Instead of passing, you pass like we're like